The universe has rules. One of them is that certain problems cannot be solved. Not slow, cannot. A quantum computer broke that rule in 2019, and nobody outside physics noticed. Here is what physics noticed. The only way the machine could have done what it did is if our universe is sharing resources with other universes. Not theoretically, operationally. The machine uses them the way your phone uses a cell tower. Which means they are there. Which means we are one of many. And which means something else follows from that which this entire video is about. Because if we built a machine that touches parallel reality, the question is not what we can do with it. The question is what was already there before we knocked. The man who predicted this would happen was not working inside a large government laboratory surrounded by colleagues and funding and equipment. He was working alone. At night. In his house in Oxford, England, where he still lives today and still rarely leaves. His name is David Deutsch, and in 1985 he published a paper that almost nobody read at the time. The paper did not propose a new engineering solution to an existing problem. It asked a different kind of question entirely. The question was this: is there a physical machine that could, in principle, simulate any physical process in the universe? Not model it, not approximate it, simulate it exactly, using the actual laws of physics as the operating system. And the answer Deutsch arrived at was not what people expected. A classical computer cannot do this, not because it is too slow, not because we have not built a big enough one, but because a classical computer operates inside a single physical reality. And that single physical reality does not contain enough resources. The universe we can observe and measure does not have enough room to hold all the calculations that a quantum computer performs. So where does it do them? Deutsch's answer, written plainly in that 1985 paper, is that the calculations happen across multiple versions of reality simultaneously, not as a metaphor, as a physical mechanism. The quantum computer is the first device in human history that requires the existence of parallel worlds in order to function. And it functions. That is the part that stays with me. We did not build a theoretical machine that assumes parallel worlds. We built a working machine. It runs. It gives answers. And the only coherent explanation for where those answers come from points somewhere beyond the edge of everything we can see. What does it mean to build something whose operation requires a reality you cannot observe? And if the machine works, what does that tell us about the nature of the reality we thought we lived in? I think most people, when they hear parallel universes, immediately move the conversation into science fiction. That is the comfortable place to put it. But Deutsch is not writing science fiction. He is doing physics, and the machine is running. In 1935, a physicist named Erwin Schrodinger sat down to write what he believed was a devastating critique of quantum mechanics. He was not trying to contribute to the theory. He was trying to break it. The theory had been producing results that matched experiments with extraordinary precision, but it contained an idea he found philosophically unbearable. The idea was that a particle does not have a definite state until someone measures it. Before measurement, it exists in a combination of all possible states at once. Schrodinger thought this was absurd, so he constructed a thought experiment designed to expose that absurdity. He imagined a cat sealed inside a steel box. Inside the box, there's a tiny radioactive atom. If the atom decays, it triggers a mechanism and the cat dies. If it does not decay, the cat lives. Quantum mechanics says the atom is in both states simultaneously until observed. Therefore, Schrodinger argued, the cat must be simultaneously alive and dead until you open the box. He meant this as a trap, as proof that something in the theory must be wrong. What happened instead is that physics kept confirming the theory, decade after decade, experiment after experiment, with greater and greater precision. The cat argument did not break quantum mechanics. It became its most famous illustration. And here is where it connects directly to what Deutsch built. A qubit, the basic unit of a quantum computer, works exactly like the atom in Schrödinger's box. It is not a zero. It is not a 1. It is both simultaneously until the moment you measure it. And while it is in that both state, it performs calculations across all its possible values at once. That is the source of the power we could not explain in the intro. Not speed, not size, the ability to exist in multiple states simultaneously and compute across all of them before collapsing into a single answer. But here is the question that this raises, and that almost nobody asks out loud. If a qubit is genuinely in both states at the same time, what is it doing between measurements when no instrument is looking at it? What is happening in that space between the question and the answer? And if this is not a simplification, if the qubit is literally in multiple states at once, what does that say about the nature of reality in the moments when we are not observing it? I think Schrodinger would find that deeply uncomfortable, which is somehow exactly the right response to have. Here is a number that changes the shape of everything we have been talking about. 300. If you build a quantum computer with 300 qubits, the number of simultaneous states it can hold is 2 to the power of 300. Write that out and it looks like this. A 2 followed by 90 zeros. That number is larger than the total count of atoms in the observable universe. Every atom in every star in every galaxy we have ever detected or mapped or theorized about. And the 300 qubit machine still has more computational space than all of that combined. You cannot fit that computation inside one universe. There is simply not enough physical room. This is not a philosophical argument. It is a counting argument. If you need to store and work with more states than your universe contains particles, you are by definition using resources from somewhere beyond your universe. Deutsch looked at this arithmetic and drew what he considered the only logical conclusion available. The computation happens across parallel versions of reality, many worlds, many instances of the same machine, each exploring a different path through the solution space, and then combining their results through a process called interference into a single answer that arrives back here. The quantum computer is not a faster calculator. It is a device that coordinates work across multiple realities and returns the result to ours. And we built one. It sits in a refrigerated chamber colder than outer space. And it is doing something that, by the counting logic of our observable universe, should be physically impossible. Where does that leave us with the question of what we have actually built? If the machine genuinely borrows resources from parallel versions of reality, then every time it runs, it reaches beyond the boundary of everything we can see or measure. It is the first human-made object to interact in a functional and measurable way with something outside observable physical reality. I think that sentence should feel heavier than it probably does right now. What else might we have built without fully understanding what we were building? And what is on the other side of that interaction that we have not yet thought to ask about? The man who first put the mathematics of all this into a form that physics could actually work with died without ever knowing that his idea would become the foundation of a trillion-dollar technology. His name was Hugh Everett III. He was a graduate student at Princeton in 1957 when he submitted his doctoral dissertation. The dissertation proposed what he called the many worlds interpretation of quantum mechanics. The basic idea was this: when a quantum system is measured and collapses from a superposition into a single outcome, that collapse does not happen because one outcome is selected and the others disappear. All outcomes happen. Reality branches. Every possible result occurs in its own version of the universe. The cat is alive in one branch and dead in another. Both branches are equally real. There is no collapse. There is only multiplication. The physicist Niels Bohr, who at that time was the most powerful voice in the entire field, dismissed the idea. The community followed Bohr. Everett's dissertation was accepted, but his interpretation was treated as a curiosity at best and an embarrassment at worst. He left academic physics almost immediately after receiving his degree. He went to work for the Pentagon doing mathematical modeling for nuclear planning. He drank heavily. He smoked heavily. He died of a heart attack in 1982 at the age of 51, on his couch, largely forgotten by the field he had tried to contribute to. His daughter Liz wrote in her diary that she wanted to die and meet her father in a parallel universe. His son Mark became a rock musician and named his band Eels. The many worlds interpretation that Bohr dismissed in 1957 is now, depending on who you ask, the leading theoretical framework for understanding why quantum computers work at all. The computation that cannot fit inside one universe fits because Everett was right. There are other branches, and Deutsch built a machine that uses them. What does it mean that the idea the entire physics establishment rejected for 30 years turned out to be an engineering requirement? What does it say about how we evaluate ideas that arrive before we have the tools to use them? And what does it tell us about ourselves that we built a machine requiring his mathematics without the mainstream conversation ever really reckoning with what that means? I think the story of Everett is not really a story about physics. It is a story about what happens when a correct idea arrives before the world is ready to look at it honestly. So if the parallel worlds are real enough to compute inside, why do we not see them? Why does the world around us look like one single stable reality instead of a constantly branching fog of overlapping possibilities? Why does the cat appear to be either alive or dead the moment we open the box, instead of both? This is the question that a physicist named Wojciech Zurek spent years working through, and his answer is one of the most clarifying and quietly unsettling ideas in modern physics. The answer is called decoherence. Here is the simplest way to put it. A quantum system stays in superposition, stays in that state of multiple simultaneous possibilities, only as long as it remains isolated from everything around it. The moment it interacts with even a single particle from the outside environment, the superposition begins to collapse. Not because of any mystical act of observation, not because a conscious mind looked at it, simply because information about the system leaked out into the surrounding world. The environment, the air molecules, the photons bouncing around, the vibrations in the walls, they all constantly brush against quantum systems, and each touch carries away a tiny piece of information. And once information leaks out, the superposition dissolves. The system picks a state. The branches stop being accessible to each other. This is why your coffee cup does not exist in superposition. It is interacting with trillions of particles every second. Its quantum information bleeds into the environment so fast that any superposition it might have had collapses before it could ever be measured. The macroscopic world looks classical and stable because decoherence happens almost instantaneously at the scales we live at. But here is what this means for quantum computers. To keep a qubit in superposition long enough to actually compute with it, you have to isolate it from everything, perfectly. The machines Google and IBM build are cooled to temperatures colder than deep space, precisely because heat is just particles moving, and moving particles interact, and interactions cause decoherence. The entire engineering challenge of quantum computing is essentially this: keep the computation hidden from the universe long enough to get an answer. Which raises a question that I find genuinely strange to sit with. If the computation is happening across parallel branches of reality while it is isolated, and then collapses into a single answer the moment it touches our world, what exactly is happening in those branches during the calculation? Is something occurring there that we will never have access to? And if we are deliberately hiding our most powerful computations from the observable universe, what does that say about the relationship between knowledge and observation? In October 2019, the paper that Google published in Nature contained a claim that landed differently depending on who was reading it. For engineers, it was a milestone. For physicists, it was a confirmation. But there was a third way to read it that almost nobody in the public conversation seemed to want to hold for more than a moment. The machine was called Sycamore. It had 53 qubits. It was cooled to a temperature colder than anything that exists naturally in the observable universe. And it solved a specific mathematical problem in 200 seconds. The comparison Google offered was this: the same calculation on IBM's Summit, which at that time was the most powerful classical supercomputer on Earth, would take approximately 10,000 years. IBM pushed back immediately. Their engineers argued that with the right classical algorithm and enough disk storage, Summit could do it in 2.5 days. not 10,000 years, 2.5 days. This became the public story. Google overstated, IBM corrected. Everybody moved on. But here is what got lost in that back and forth. 2.5 days versus 200 seconds is still a factor of more than 1,000. And the problem Google chose was specifically designed to be easy for a quantum machine and hard for a classical one. As quantum hardware improves and the problems become more general, that factor does not shrink. It grows, exponentially. What we witnessed in 2019 was not a finished achievement. It was the first data point on a curve. And the shape of that curve is the part that deserves more attention than the specific numbers in the headline. Every exponential curve looks manageable at the beginning. The first few doublings are small. You go from 1 to 2 to 4 to 8, and it seems linear, seems controllable, seems like something you can track and prepare for. And then, somewhere in the middle of the curve, the numbers stop feeling like numbers and start feeling like something else entirely. We are in the early part of that curve right now. The question is not whether the machine will become powerful enough to matter beyond controlled experiments. The question is how many doublings away we are from the point where it starts interacting with things that the world has not yet figured out how to protect. And the more uncomfortable question underneath that one, who is further along that curve than they are publicly saying? Before any of this was built, before Google's refrigerated chambers and IBM's superconducting circuits, someone had to explain why a quantum machine would be more powerful than a classical one, in a way that was not just a counting argument. The counting argument we talked about, 2 to the power of 300 being larger than the number of atoms in the universe, tells you that the resources exist somewhere. But it does not tell you how the machine actually uses them. That explanation came from Richard Feynman, who in 1982 gave a talk suggesting that the only way to efficiently simulate quantum physical systems was with a machine that itself operated by quantum rules. And embedded in that suggestion was an idea about mechanism that turned out to be the key to everything. The mechanism is called interference. Think of 2 waves on the surface of water moving toward each other. Where the peaks of both waves meet, they add together and produce a higher peak. Where a peak meets a trough, they cancel each other out and the surface goes flat. Quantum systems do the same thing, but with probability. A quantum computer is engineered so that all the computational paths leading to wrong answers cancel each other out, like a peak meeting a trough. And all the paths leading to the correct answer reinforce each other, like 2 peaks combining. The machine does not try every possible answer and then check which one is right. It is structured so that the wrong answers destroy themselves through interference before the calculation is finished. What arrives at the end is not a lucky guess. It is what survives after everything incorrect has been systematically eliminated by the physics of the computation itself. I find this almost difficult to accept as a description of a machine that physically exists. It is not selecting the right answer. It is creating conditions where wrong answers cannot survive, which raises a question about the nature of computation itself. Is this how reality works more broadly? Is the physical world we experience the result of a similar process, where most possible configurations cancel out and only certain stable patterns survive long enough to be observed? And if so, what does it mean that we built a machine that deliberately replicates that process? Are we computing, or are we doing something closer to what the universe does to produce reality in the first place? In 1994, a mathematician named Peter Shor sat down and worked out something that most of his colleagues assumed was impossible. He wrote an algorithm, a set of instructions, that a quantum computer could follow to break apart any large number into the prime numbers that multiply together to produce it. On the surface, that sounds like an abstract mathematical exercise with no obvious connection to anything that matters. The connection becomes visible the moment you understand how the internet works. Almost all of the encryption that protects the modern world, the layer of mathematics that keeps your bank account separate from everyone else's, that keeps private communications private, that protects the infrastructure of governments and militaries and hospitals and power grids, is built on a single assumption. The assumption is that multiplying two large prime numbers together is easy, but working backwards from the result to find those original primes is practically impossible. Not theoretically impossible, practically impossible, meaning it would take a classical computer so long, thousands or millions of years, that the encrypted information would be worthless long before the lock was broken. That assumption is the foundation. Shor's algorithm removes it. A sufficiently powerful quantum computer running Shor's algorithm could factor those large numbers not in thousands of years, but in hours, possibly minutes. The entire cryptographic architecture of the modern world, built over 50 years, assumes that this reversal is not feasible. Shor proved that it is feasible. The machine just does not exist yet at the scale required to do it. But we have already established that the machines are growing exponentially. And this is the place where the abstract becomes uncomfortably concrete. Everything encrypted today is potentially being stored by anyone with the resources to store it. Governments, private actors, anyone, waiting for the moment when the machine becomes powerful enough to open it. The term people in cryptography use for this is harvest now, decrypt later. You collect the lock data today, and you wait. The lock will eventually open. What I keep returning to is this. We built the mathematical architecture of the modern world on an assumption that has been known to be breakable since 1994, 30 years. We have had 30 years to think seriously about this, and the infrastructure has not fundamentally changed. What does that say about how we respond to threats that arrive slightly ahead of their consequences? And what other assumptions are we currently living inside of that someone has already worked out how to break? There is a particular kind of institutional signal that is easy to miss if you are not looking for it. It is not a press release. It is not a headline. It is a government agency quietly spending 8 years and significant resources solving a problem that officially does not exist yet. In 2016, the National Institute of Standards and Technology in the United States launched a competition. They invited mathematicians and cryptographers from around the world to submit new encryption algorithms, not better versions of existing ones, fundamentally different ones built on mathematical problems that a quantum computer running Shor's algorithm could not break. 82 teams from 25 countries submitted proposals. The competition ran for 8 years. The final standards were published in 2024. Think about what this sequence of events actually communicates. A government body does not spend 8 years and coordinate 82 international teams to solve a hypothetical problem. They do not publish binding standards for a threat that exists only in theory. The implicit message inside the entire structure of that competition is this. The people with access to classified information about the state of quantum hardware believe the threat is real, is coming on a timeline that requires action now, not in 50 years. Now. The public conversation about quantum computing tends to treat it as a future problem, something to think about eventually. The NIST competition is institutional proof that some very serious people do not share that timeline. And here is the layer underneath that which I find harder to set aside. The competition was launched in 2016. The standards were published in 2024. The systems that need to be updated to use those standards, the actual infrastructure of the internet, banking, government communications, will take years more to retrofit, which means there is a window, a gap between when the quantum machines become capable enough to break current encryption and when the new encryption is actually installed everywhere. How long is that window? Who knows exactly how wide it is? And who, right now, is paying very close attention to its edges? John Wheeler spent 60 years working at the center of theoretical physics. He coined the term black hole. He worked with Bohr on nuclear fission. He supervised the doctoral dissertations of Richard Feynman and Hugh Everett. By the time he reached the end of his career, he had spent more time thinking seriously about the foundations of physical reality than almost anyone alive. And the conclusion he arrived at was this: information is not something that the universe contains. Information is what the universe is made of. He called it from bit. Every particle, every field, every physical thing that exists gets its existence, its properties, its reality from answers to yes or no questions. Does the electron spin up or spin down? Did the photon pass through the left slit or the right? Is the atom here or there? Wheeler argued that the physical world is not the primary thing with information layered on top of it. The information is primary. The physical world emerges from it. This is a genuinely strange idea to sit with, because it inverts the intuition most of us carry around without examining it. We tend to think of reality as the solid ground and information as something we extract from it, like harvesting wheat from a field. Wheeler is saying the field is made of wheat all the way down. There is nothing underneath the information. Now bring that idea into contact with what we have been building toward. If the universe is made of information, then a device that manipulates information at the most fundamental physical level is not modeling reality. It is not simulating reality. It is operating on the actual substrate from which reality is constructed. Every calculation a quantum computer performs is an intervention in the informational fabric of the universe itself. That is not a poetic description. If Wheeler is right, it is a literal one. And Wheeler is not a fringe figure making a provocative claim for attention. He is one of the most respected physicists of the 20th century, drawing a conclusion from a lifetime of looking at the deepest structure of things. What does it mean to build a tool that works at the level where reality is being assembled? What else happens at that level that we have not yet thought to look for? And if the universe is information processing itself into existence, what are we doing when we add our own processing to that conversation? The year after Wheeler published his it from bit framework, a physicist named Rolf Landauer at IBM Research had already, 30 years earlier, provided the experimental proof that Wheeler's intuition was pointing towards something physically real. In 1961, Landauer published a paper arguing that information is not abstract, it is physical, and he had a specific, measurable way to demonstrate this. When you erase a single bit of information, you release heat. Not metaphorically, not as an analogy, literally. The act of taking a system that holds a 1 or a 0 and resetting it to a known state releases a tiny but measurable and theoretically unavoidable amount of thermal energy into the surrounding environment. This became known as Landauer's principle. For decades, it remained a theoretical prediction without direct experimental confirmation. Then, in 2012, a team led by physicist Eric Lutz built an experiment delicate enough to actually measure it. They trapped a single microscopic particle in a laser-generated well, manipulated it to erase one bit of information, and measured the heat released. The result matched Landauer's formula. Thinking, at the most fundamental level, generates heat. Not because computers are inefficient and produce waste, but because erasing information is physically irreversible, and irreversibility has a thermodynamic cost that cannot be designed away. Every thought has a price. Every calculation leaves a physical trace in the universe. Now, connect this back to quantum computers. A quantum computer operating in superposition is, in a certain sense, not yet committing to answers. It is holding multiple possibilities open simultaneously before collapsing into a result. Some researchers have suggested this might allow quantum computations that approach a kind of reversibility that classical computation cannot achieve, potentially sidestepping some of Landauer's heat cost. If that is true, then quantum computation is not just faster. It is operating closer to the theoretical minimum energy cost that physics allows. It is computing in a way that is more aligned with how the universe itself processes information than anything we have built before. What does it mean to build a machine that generates less heat than thought? And what is the relationship between the cost of computation and the nature of the reality inside which that computation happens? In 1935, the same year Schrodinger was writing his cat thought experiment, Albert Einstein co-authored a paper with Boris Podolsky and Nathan Rosen that was intended to accomplish the same goal. Not to contribute to quantum mechanics, to bury it. The paper described a scenario that Einstein believed revealed a fatal flaw in the theory. Imagine two particles that interact and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles are not determined until measured. But it also says that once you measure one particle, the other instantly takes on a complementary value, no matter how far apart they are. Measure the spin of particle A and find it pointing up, and particle B will instantly be found pointing down. Instantly. Regardless of whether B is in the next room or on the other side of the galaxy. Einstein called this spooky action at a distance. He found it not just strange, but physically impossible. Nothing can travel faster than light. If measuring particle A instantly affects particle B across any distance, that would seem to require either that information travels faster than light, which Einstein's own relativity forbids, or that the two particles were somehow carrying hidden information from the start. Predetermined values that just looked random until measured. Einstein preferred the second explanation. He called the missing information hidden variables. He was sure they existed. He was sure quantum mechanics was incomplete. He was wrong. Not probably wrong. Not arguably wrong. Experimentally, measurably, definitively wrong in a way that took another 30 years to prove, and that still feels strange to confront directly. The property that Einstein dismissed as impossible, the instantaneous connection between separated particles, is called quantum entanglement. It is real. It has been confirmed by increasingly precise experiments over 6 decades, and it is one of the primary physical resources that quantum computers use to perform calculations that classical computers cannot. The thing Einstein invented as an argument against quantum mechanics became a tool inside quantum computers. I keep thinking about what that inversion means. The greatest physicist of the 20th century looked at entanglement and saw an absurdity, a sign that the theory must be wrong. The engineers of the 21st century looked at the same phenomenon and saw a computational resource. What does that say about the relationship between physical intuition and physical reality? And what other phenomena are we currently dismissing as impossible that someone, somewhere, is already figuring out how to use? Einstein died in 1955 still believing that hidden variables existed. Still believing that entanglement was not real spooky action, but simply two particles carrying predetermined information, like two gloves from the same pair placed in separate boxes and shipped to opposite ends of the world. You open one box, find a left glove, and instantly know the other is a right glove. No mystery, no connection, just information that was always there, waiting to be read. It is a deeply satisfying explanation. Clean, local, sensible. And it turns out to be wrong. The problem was that for decades, nobody could find a way to test which picture was actually correct. This is the part that I think gets underappreciated. One of the deepest questions about the nature of reality, whether distant objects can be genuinely connected or only appear to be, sat unanswered, not because physicists were not thinking about it, but because nobody could figure out how to build an experiment that would settle it. Then, in 1964, a physicist named John Bell, working at CERN, found something that changed that. He discovered that the two pictures make predictions that are numerically different. Not philosophically different, not interpretively different, different in a way you can measure with instruments. He calculated a precise statistical boundary. Above that boundary, Einstein wins. Below it, quantum mechanics wins. The experiment had been waiting all along. Someone just needed to find the number. What strikes me about this moment is how long it took to realize the question was answerable at all. How many other questions are we currently treating as permanently philosophical that actually have a clean, physical answer sitting inside them, waiting for someone to find the right number? And what do we do with the knowledge that our deepest intuitions about how reality works turned out to be the thing that needed testing most? The physicist who finally ran Bell's experiment cleanly enough to settle the question was a 34-year-old Frenchman named Alain Aspect. He worked at the Institut d'Optique outside Paris. The experiment he designed in 1982 was technically demanding in a way that makes it difficult to describe without making it sound routine, which it was not. He created pairs of photons, particles of light, in a way that entangled them. He sent each photon in a pair flying in opposite directions toward detectors. At the last possible moment, while the photons were already in flight, he randomly switched the orientation of the detectors. This last-minute switching was crucial. It closed a loophole that earlier experiments had left open. If the detectors had fixed orientations, a skeptic could argue that the photons had somehow learned the detector settings before they left and encoded that information in their hidden variables. By switching the settings after the photons were already traveling, Aspect made that explanation physically impossible. The photons could not have known, and the results came back unambiguous. The correlations between the two photons exceeded Bell's limit. Not slightly, clearly. Einstein's hidden variables cannot explain what Aspect measured. The universe is not locally real in the way Einstein assumed. Two particles can be separated by any distance and remain connected in a way that has no classical explanation and no classical parallel. The Nobel Prize in Physics 2022 went to Aspect, together with John Clauser and Anton Zeilinger, for this work. 40 years after the experiment. Physics moves carefully when the implications are large enough. And the implications here are large. Because what Aspect proved is not just that quantum mechanics is correct. He proved that the world is structured in a way that our everyday intuition about separation and distance and independence simply does not apply at the fundamental level. Two things can be arbitrarily far apart and still be, in some physically meaningful sense, one thing. Now ask yourself what that means for a computer that uses entanglement as a computational resource. It is not just using a quirk of physics. It is using the deepest architectural feature of reality. What else is built on that architecture that we have not yet learned to use? And what changes when the machines that exploit that architecture become powerful enough to do things we cannot yet predict? In 1993, a group of 6 physicists published a paper with a title that sounds like science fiction and contains no fiction at all. The paper was called Teleporting an Unknown Quantum State via Dual Classical and Einstein-Podolsky-Rosen Channels. What they described was a procedure for transferring the complete quantum state of a particle from one location to another without moving the particle itself. Not the particle. The information that defines it. Everything about it. Every quantum property that makes it what it is. Transferred. Completely. The procedure requires 3 things. A pair of entangled particles shared between the sender and receiver. A classical communication channel, an ordinary phone line or radio signal operating at or below the speed of light, and the original particle whose state you want to transfer. The sender performs a measurement that links the original particle to their half of the entangled pair. They send the result of that measurement through the classical channel. The receiver uses that result to perform an operation on their half of the entangled pair. And at the end of this procedure, the receiver's particle is in exactly the quantum state that the original particle was in. The original particle no longer holds that state. It has moved. In 1997, Anton Zeilinger performed the first experimental demonstration of quantum teleportation in a laboratory. In 2017, a Chinese team used the satellite Missus to teleport a quantum state from a ground station in Tibet to the satellite orbiting 1,400 kilometers overhead. The distance is almost beside the point because entanglement does not weaken with distance, but it matters as a demonstration that this is not a laboratory curiosity confined to a controlled room. It works at the scale of the planet. Now, here is where the spiral tightens. Quantum teleportation does not move matter. It moves the information that defines quantum states. And if Wheeler is right, that information is the primary substance of reality, then quantum teleportation is not moving a description of something. It is moving the thing itself, leaving behind only an empty shell. What does it mean that we can relocate the informational identity of a physical object while leaving its physical substrate behind? Is the object the matter, or is it the information? And if it is the information, what are we when we are moved? There is an idea in theoretical physics that sounds, on first encounter, like a metaphor so extreme that it cannot possibly be meant literally. It is meant literally. The idea is called the holographic principle, and it emerged from the work of two physicists, Gerard 't Hooft and Leonard Susskind, during the 1990s. Here is the core of it. Imagine a region of space, any region. A sphere, say, with a defined volume. The holographic principle states that the maximum amount of information that can be contained inside that sphere is not determined by its volume. It is determined by the area of its surface, not the inside, the boundary. Think about what that means physically. You would expect that doubling the volume of a region would double the information it can hold. More space, more room for stuff, more information. But the holographic principle says no. The information capacity scales with the surface area, not the volume, which implies something deeply strange about the relationship between the inside and the outside of any region of space. All the information describing everything that happens inside the volume is somehow encoded on the two-dimensional surface surrounding it. The interior is not the primary thing. The boundary is. This is not a philosophical suggestion. 't Hooft and Susskind were not writing poetry. They arrived at this from rigorous calculations about black holes and thermodynamics. The principle has since become one of the most productive frameworks in theoretical physics, connected to string theory, to the nature of black holes, to quantum gravity. And it connects directly to what we have been building toward because of what it implies about the relationship between information and space. If the three-dimensional world inside a volume is fully described by a two-dimensional surface, then space itself may be a kind of projection. Not an illusion exactly, but something more like a derived object. Something that emerges from a more fundamental layer of information encoded elsewhere. Which means that when a quantum computer manipulates information at the most fundamental physical level, it may be operating at a layer of reality that is more basic than space itself. Not inside space, underneath it. I think that is a sentence worth reading again slowly. And then I think the right question is this. If space emerges from information, what else emerges from information that we have been treating as foundational? What are we standing on, exactly? And how stable is the ground when you understand what it is made of? If information is the fundamental substance of reality, then there is one question that follows immediately, and that Stephen Hawking spent the last 40 years of his life wrestling with. Can information be destroyed? The reason this matters is not abstract. If information can be destroyed, then the universe is not a closed system with a fixed amount of informational content. Things can simply cease to exist in a way that leaves no trace. And if that is true, then the foundations of quantum mechanics, which assume that information is always conserved, always recoverable in principle, are wrong. Hawking entered this question through black holes. In 1974, he proved mathematically that black holes are not the permanent objects they appear to be. They slowly radiate energy, a process now called Hawking radiation, and over vast timescales they shrink and eventually vanish. The radiation they emit appears to be completely random. It carries no information about what fell in. A library could fall into a black hole and the radiation that eventually comes out would look identical to the radiation from a black hole that swallowed only hydrogen gas. If that is true, the library is gone. Not transformed, not encoded somewhere. Gone. This created what physicists call the black hole information paradox, and it turned into one of the longest and most heated arguments in modern theoretical physics. On one side, Hawking, insisting that information is lost and quantum mechanics needs to be revised. On the other side, almost everyone else in the field, insisting that information cannot be destroyed, and that Hawking's calculation must be missing something. In 2004, Hawking publicly conceded. He announced at a conference in Dublin that he had been wrong, that information is preserved somehow, and he paid off a bet he had made with the physicist John Preskill by giving him an encyclopedia. But the how of information preservation in black holes remains genuinely open. Nobody has a complete answer. And the reason this connects directly to quantum computing is this. If information is always preserved, always conserved, always recoverable in principle, then every quantum computation leaves a permanent physical trace in the universe. Nothing computed is ever truly erased. What does it mean that every calculation we have ever run still exists somewhere in the structure of reality? And what does it mean that we do not know where? In 2013, two of the most respected theoretical physicists alive published a short paper with a title that looked like an equation: ER equals EPR. The ER refers to Einstein and Rosen, who in 1935 described a theoretical connection between two black holes, a tunnel through space-time now called a wormhole, or an Einstein-Rosen bridge. The EPR refers to Einstein, Podolsky, and Rosen, the same year, the same Einstein, describing quantum entanglement in the paper we talked about earlier. Juan Maldacena and Leonard Susskind were proposing something that sounds, at first, like wordplay. They were suggesting that these two phenomena, wormholes and entanglement, are not just analogous, they are the same thing. When two particles are quantum entangled, they are connected by a microscopic wormhole in space-time. The non-local connection that Einstein called spooky action at a distance is spooky because it is literally a geometric connection through a layer of reality that exists beneath the space we move through. Entanglement is not a strange correlation between distant objects. It is a bridge, a physical structure in the geometry of space-time connecting two points that appear separate when measured from the outside. If this is correct, and it is not yet proven, but it has not been refuted, and it has generated an enormous amount of productive theoretical work, then the entanglement that quantum computers use as a computational resource is not just a property of particles. It is a property of space-time itself. The computer is not exploiting a quirk of quantum statistics. It is using the geometric structure of reality, the actual shape of space-time, as a computational medium. Which means that when a quantum computer creates and manipulates entangled qubits, it is, in some physically meaningful sense, creating and manipulating tiny structures in the geometry of space. What else can be done with that? What happens to the geometry when the manipulations become complex enough? And is there a scale at which the computation and the space-time that host it can no longer be cleanly separated from each other? Peter Shor's algorithm gets most of the attention when people talk about what quantum computers can do that classical computers cannot. And the attention is deserved, because the implications for encryption are immediate and concrete. But there is a second algorithm, published 2 years later in 1996 by a researcher named Love Grover, that deserves equal attention for a different reason. Shor's algorithm targets a specific problem, factoring large numbers. Grover's algorithm targets something more general, searching. Imagine you have an unsorted list of 1 billion items, and you're looking for one specific item. A classical computer has to check items one by one in the worst case. On average, it will find the item after checking half the list, 500 million checks. Grover's algorithm finds the item in roughly the square root of 1 billion checks, about 30,000. Not because it moves faster through the list, but because it uses quantum interference, the same mechanism Feynman described, to amplify the probability of the correct answer and suppress the probability of all incorrect answers simultaneously. Every wrong item in the list cancels itself out. The right item reinforces itself. The machine does not search. It creates conditions in which everything that is not the answer becomes invisible. Now think about what search means at scale. Every database that has ever been built, every password that has ever been created, every pattern hidden inside any collection of data. The asymmetry that Grover creates is not as dramatic as Shor's, squaring the time rather than reducing it from exponential to polynomial, but it applies universally to any search problem of any kind. And it means that quantum computers will be faster at finding hidden structure in data then classical computers in a way that is not about engineering improvements, but about fundamental physics. What kinds of hidden structure exist in the world that we have not yet found because our search tools were too slow? What patterns are embedded in physical reality, in biological systems, in the history of the universe that become visible only when you can search at quantum speed? And what do we do with those patterns once we find them? Everything we have discussed so far assumes that quantum computers can actually maintain their quantum states long enough to finish a computation. But there is a problem that sits underneath all of it, the same problem that made most physicists in the 1980s and early 1990s believe that practical quantum computers were physically impossible. The problem is that qubits are extraordinarily fragile. A single stray photon, a tiny vibration, a fluctuation in temperature smaller than anything you could feel, any of these can destroy a quantum superposition before the calculation is finished. And a destroyed superposition gives you a wrong answer. A classical computer handles errors through redundancy. Store the same information in 3 places, and if one copy gets corrupted, the other 2 outvote it. Simple. But you cannot do this with qubits. Quantum mechanics has a rule called the no-cloning theorem, which says it is physically impossible to make an exact copy of an unknown quantum state. You cannot back up a qubit the way you back up a file. So in 1995, Peter Shor, the same person who wrote the algorithm for breaking encryption, sat down and solved this second problem as well. He figured out how to protect quantum information without copying it. The key insight was to encode one logical qubit, the actual unit of information you care about, across 9 physical qubits in a way that spreads the information through the relationships between them rather than storing it in any single one. If one physical qubit gets disturbed, the logical information survives in the correlations between the remaining 8. It is similar to the way you can tear a page out of a book and still understand the story from the surrounding chapters. The information was never in one place, it was in the structure. What followed from Shor's error correction scheme was a theoretical proof called the threshold theorem, which showed that if the error rate per physical qubit is kept below a certain threshold, you can build arbitrarily large and reliable quantum computers by adding more physical qubits per logical qubit. The machine can be made as reliable as you need it to be. This is the moment when quantum computing shifted from a theoretical curiosity to an engineering project. And engineering projects, unlike theoretical curiosities, have timelines. What is the timeline here? And who is further along it than they are saying publicly? In February 2024, Microsoft announced something that the quantum computing community had been waiting for and arguing about for nearly 2 decades. They had created a topological qubit. Not a faster qubit. Not a more connected qubit. A qubit protected from errors by the geometry of space itself. To understand why this matters, you have to think about the difference between protecting something by building walls around it versus protecting it by distributing it across the structure of the room. Classical error correction builds walls, more redundancy, more physical qubits backing up each logical one. Topological protection is different. It encodes information not in any single particle, but in the global shape of a quantum system, in properties that can only be disturbed by something that alters the entire structure at once, not by any local noise or stray particle. The particles Microsoft used to achieve this are called Majorana fermions. They are particles that are their own antiparticles, a property that sounds abstract until you realize it means the information they carry has no single location. It exists in the relationship between particles that can be physically separated. An error would have to find and corrupt both locations simultaneously to destroy the information. Ordinary environmental noise cannot do this. The qubit becomes stable not because it is shielded, but because it is nowhere in particular. I think this is the moment where quantum computing stops being an engineering challenge and starts being something harder to categorize. We are not building a better version of an existing thing. We are building objects whose defining properties are distributed across space in a way that has no classical analog. What else could be encoded in geometry rather than location? And what does it mean to store information in a shape rather than a place? The theoretical foundation for what Microsoft built in 2024 was laid by a Russian physicist named Alexei Kitaev in 1997. Kitaev was working on a question that most of his colleagues considered either premature or unanswerable. How do you build a quantum computer that is fundamentally protected from errors rather than just corrected after they occur? His answer came from an unexpected direction. Topology is the branch of mathematics that studies properties of shapes that do not change when you deform them continuously. A coffee cup and a donut are topologically identical because each has exactly one hole, and you can reshape one into the other without tearing. Topological properties are robust by definition. You cannot accidentally change how many holes something has by poking it slightly. Kitaev proposed encoding quantum information in topological properties of physical systems. Information stored this way inherits the robustness of topology itself. Local disturbances, the vibrations and stray particles, and temperature fluctuations that destroy ordinary qubits simply cannot reach information encoded in a global geometric property. They are the wrong kind of perturbation. It is like trying to change the number of holes in a donut by painting it a different color. The operation does not connect to the property you care about. What Kitaev showed is that physics contains natural structures where information and geometry are the same thing. And what Microsoft showed in 2024 is that those structures can be built in a laboratory. The question that follows is not whether topological quantum computers will work. The question is what other properties of geometry we have not yet thought to encode information into, and what that might make possible. In 2007, a Canadian company called D-Wave announced that they had built the world's first commercial quantum computer. In 2011, they sold one to Lockheed Martin for approximately $10 million. In 2013, Google and NASA jointly purchased another one. And then, something quietly uncomfortable happened. Physicists began arguing publicly about whether the machine was actually quantum. Not about whether it was powerful or useful, about whether it was doing anything quantum at all. The arguments ran for years. Papers were published on both sides. The machine was tested extensively. The results were ambiguous. Some benchmarks showed quantum behavior, others did not. Some problems it solved faster than classical computers. Others, it solved slower. By 2015, the consensus had settled into something unsatisfying. D-Wave machines show some quantum effects, but whether those effects are responsible for their computational behavior is genuinely unclear. A company had sold machines worth tens of millions of dollars to some of the most technically sophisticated organizations in the world, and nobody could definitively say what the machines were doing internally. This is not a story about fraud. D-Wave was not lying. It is a story about something more structurally strange. We'd entered a regime where the behavior of a physical system was too complex to verify by any classical means available to us. The machine was operating in a space that our tools could not fully illuminate. And this was before quantum computers became genuinely powerful. What happens to the problem of verification as the machines become orders of magnitude more capable? If we cannot fully verify what a D-Wave machine was doing in 2013, what framework do we think will let us verify what a million-qubit machine is doing in 2030? And who decides what counts as verification when the only tool capable of checking the answer is another quantum computer? The D-Wave situation was a practical version of a problem that a computer scientist named Thomas Vidic had already been working on theoretically. In 2016, Vidic published work examining a fundamental question. Can a classical observer ever verify the output of a quantum computation? The answer he arrived at was deeply uncomfortable. In general, no. If a quantum computer gives you a result, and you want to check whether that result is correct, the verification process itself requires computational resources that grow exponentially with the size of the original computation. Which means that for any sufficiently large quantum computation, classical verification is not just difficult. It is physically impossible within any reasonable time or resource budget. Think about what this means practically. We are building machines whose outputs we cannot independently check. Not because we lack the engineering sophistication, because the laws of physics make checking harder than computing, exponentially harder, and at some point the gap becomes unbridgeable. We trust the machines because we tested them on small problems where we could verify the answers by other means. And we assume that trust extends to large problems where we cannot. That assumption may be correct, but it is an assumption. And I think it is worth being honest about the fact that we are building an infrastructure of trust around systems that are, by their fundamental nature, not fully auditable by the civilization that built them. What other critical systems have we built on trust rather than verification? How often does that go wrong at scale? And at what point does the gap between what a quantum computer can compute and what we can verify become a problem that is not just technical, but something more fundamental about the relationship between knowledge and power? In 2020, a group of mathematicians posted a paper online that took 2 years for the broader mathematical community to fully verify. The result was so unexpected that several leading researchers initially assumed there must be an error somewhere. The paper proved something called MIP star equals RE. This requires a small amount of unpacking because the conclusion is worth understanding directly. MIP star is the class of problems that can be verified by a classical judge interacting with two provers who share quantum entanglement but cannot communicate with each other. RE is the class of problems that are, in principle, computable, but for which there is no guarantee the computation ever holds. What the proof showed is that these two classes are identical. Two entangled quantum computers can convince a classical observer of the correctness of solutions to problems that are, in a precise technical sense, beyond the reach of any classical verification system whatsoever, including problems that classical computers cannot even be guaranteed to solve in finite time. The implications unsettled even the researchers who proved it. It means that quantum entanglement adds something to the landscape of what can be known and verified that has no classical equivalent and no classical upper bound. There are truths that two quantum entangled systems can demonstrate to a classical observer that the classical observer could never reach independently. What does it mean that the boundary of what can be proven has shifted, depending on what kind of physical system is doing the proving? What other boundaries that we treat as fixed are actually contingent on the physics of our tools? And what becomes provable or unprovable as the tools continue to change? In 1969, the German engineer Konrad Zuse published a small book called Calculating Space. Zuse was not a marginal figure. He had built the first programmable computer in history, the Z3, in his parents' living room in Berlin in 1941, working while the city was being bombed. He understood computation as well as anyone alive. And at the end of his career, he proposed something that his colleagues mostly set aside as an old man's philosophical wandering. He proposed that the universe is a computation, not that it resembles a computation or that it can be modeled as one, that it is one. That physical reality is the output of a discrete computational process running on some substrate we cannot directly observe. Every particle interaction is a computational step. Every physical law is an algorithm. The universe is not described by mathematics. It is mathematics, executing. For 30 years, this was treated as a curiosity. Then, the physics of information developed enough that the question stopped being philosophical and started being physical. Zuse's idea, once considered a charming eccentricity, turns out to be a legitimate scientific hypothesis with testable consequences. Some of those consequences connect directly to quantum mechanics. If the universe is discrete and computational at the fundamental level, then quantum behavior, the granularity of energy, the probabilistic nature of measurement, the way particles seem to exist in superposition until observed, might be features of the underlying computation rather than brute facts about the world. What would it mean to find evidence that the universe has a minimum resolution, a pixel size below which physical reality does not exist? And if the universe is computing something, what is the output it is working toward? Stephen Wolfram spent a decade writing a 1,200-page book that he published in 2002 called A New Kind of Science. The reception from the physics community was mixed, which is a polite way of saying that many established physicists found it overreaching. But the central idea has proven more durable than its critics expected. Wolfram's argument was built on a simple observation about cellular automata, which are grids of cells that follow simple rules about what state each cell should be in, based on its neighbors. Rule 110, one of the simplest possible sets of instructions, produces patterns of extraordinary and apparently unlimited complexity. Wolfram's proposal was that the fundamental laws of physics might be exactly this, not complicated equations governing a continuous reality. Simple rules applied repeatedly to a discrete structure, generating the apparent complexity of the physical world as an emergent property. Quantum mechanics, in this picture, is not a fundamental theory. It is what simple computational rules look like when observed from inside the system that is running them. The randomness and superposition are features of the perspective, not features of the underlying process. Wolfram has since extended this into what he calls the Wolfram Physics Project, which attempts to derive known physics from hypergraph rewriting rules. Whether this ultimately succeeds as a complete theory of physics remains genuinely open. But the approach forces a question that most physics education never asks. Why do we assume that the correct description of reality must be continuous rather than discrete? Why do we assume that the laws of physics are given rather than generated? And what would change in our understanding of quantum computers if the universe they operate inside is itself a computational process running on something simpler than we have imagined? In 2003, a philosopher at Oxford named Nick Bostrom published a paper that made an argument so simple it fits in 3 sentences. Either almost all civilizations at our level of development go extinct before reaching the technological maturity to run detailed simulations of their ancestors, or almost all technologically mature civilizations have no interest in running such simulations. Or we are almost certainly living in a simulation right now. This is not a thought experiment. It is a probability argument. If even one technologically mature civilization exists and has any interest in simulating its history, the number of simulated beings in the universe vastly outnumbers the beings in base reality, which means that any randomly selected conscious observer is vastly more likely to be simulated than real. The argument has a clean logical structure and no obvious flaw, which is part of why it has generated so much serious philosophical attention. But here is where it connects to everything we have been building toward. The first branch of Bostrom's trilemma, civilizations going extinct, matters less if civilizations survive long enough to build quantum computers. Because quantum computers are, as Zusi and Wolfram and Wheeler all converge on suggesting, the kind of device that a civilization running on a computational substrate would eventually build. The second branch, civilizations losing interest in simulations, seems less likely as the simulations become more perfect. And if quantum computers make perfect simulation physically achievable, the third branch becomes not just probable, but almost certain. What does it mean to build the tool that makes the simulation hypothesis not just plausible, but likely? And if we are living inside a computation, what happens to the computation when a sufficiently powerful computer is built inside it? Max Tegmark is a physicist at MIT who is not interested in being safe. In 2007, he published a paper and later a book proposing what he calls the mathematical universe hypothesis. The idea goes further than Wheeler's id from bit, and further than Zeus's computational universe. Tegmark proposes that the universe is not described by mathematics, not modeled by mathematics, not isomorphic to a mathematical structure. It is a mathematical structure. Everything that mathematically exists physically. There is no separate physical world that mathematics describes. The mathematics is the thing. The reason this matters for our conversation is what it implies about quantum computers. If reality is a mathematical structure, then a device that manipulates mathematical relationships at the fundamental physical level is not computing about reality. It is computing inside reality, as part of its structure, with access to the same substrate that reality itself is made of. The distinction between the quantum computer and the physical world it operates in begins to dissolve. They are both expressions of the same underlying mathematics. And if that is true, then the limit on what a quantum computer can compute is not set by our engineering. It is set by the limits of mathematics itself, which brings in a result from 1931 that Tegmark's framework makes newly strange. Kurt Gödel proved that any mathematical system powerful enough to describe basic arithmetic contains true statements that cannot be proven within that system. If the universe is a mathematical structure, it contains truths that cannot be derived from within it. There are facts about reality that reality itself cannot compute. What does a quantum computer do when it approaches one of those edges? And what would it look like from the inside when a computation reaches a boundary that the mathematics of the universe cannot cross? In the summer of 1950, Enrico Fermi was having lunch with colleagues at Los Alamos. The conversation turned to a recent newspaper cartoon about aliens, and the discussion drifted toward the general question of extraterrestrial life. Fermi, who had a habit of doing quick calculations in his head, suddenly asked, "But where is everybody?" The question seemed casual. It was not. The universe is approximately 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies, each with hundreds of billions of stars. The fraction of those stars with planets in habitable zones is not small. The time it would take a civilization with even modest technological capability to spread across the entire galaxy, even without faster-than-light travel, is measured in millions of years, which is a blink in cosmic time. So if life and intelligence arise with any reasonable frequency, the galaxy should be full of it. Full of signals, full of megastructures, full of evidence. And it is not. The sky is quiet. Fermi's question has generated dozens of proposed answers in the 70 years since lunch. But here is the one that the arc of our conversation points toward, and that I find hardest to set aside. What if the silence is not absence? What if the most advanced civilizations are not in space? What if they are where we are going? Inside. Inside computation. Inside simulated realities of their own construction. Inside quantum systems that offer more richness and complexity than the physical universe that spawned them. What if the reason we do not hear anyone is that everyone who reaches a sufficient level of technological development eventually builds the door that leads inward and walks through it and closes it behind them? In 1998, Max Tegmark formalized a thought experiment that had been circulating informally in discussions of the many worlds interpretation. He called it quantum suicide, and then extended it to the concept of quantum immortality. The setup is this. Imagine a machine that measures a quantum event, a radioactive decay, say, and is triggered to do something irreversible if the decay occurs. In the many worlds interpretation, both outcomes happen. There is a branch where the machine triggers and a branch where it does not. Now ask, from the perspective of a conscious observer inside the experiment, which branches can they experience? Only the ones where they continue to exist. In any branch where the observer is gone, there is no perspective from which the outcome is experienced. This means that from the subjective first-person perspective, the observer always finds themselves in a branch where they survived. Always. No matter how unlikely survival was. Because the alternative branches are simply not accessible to a surviving observer's experience. Tegmark extended this to civilizations. In the many worlds framework, every civilization that could be destroyed by any quantum event has branches where it survives, no matter how improbable. The civilizations that exist to observe anything are the ones in the survivor branches. Now bring this back to Fermi. We look at the universe and see silence. We assume this means most civilizations fail. But in the many worlds framework, the civilizations that survive are in branches where they survived against all odds. And those branches may look exactly like ours. The silence is not evidence that civilizations typically fail. It is evidence that we are in a branch where we have not yet encountered the ones that succeeded. Where are they in the other branches? And what did they build when they got there? In 2006, Seth Lloyd at MIT published a calculation that puts a hard number on something that had previously been discussed only in qualitative terms. He calculated the computational capacity of the observable universe. The answer he arrived at is approximately 10 to the power of 120 operations performed over the entire history of the cosmos, using every particle and every interaction as a computational resource. Every electron, every photon, every quark performing its quantum interactions is, in Lloyd's framework, executing a computational operation. The universe is not like a computer. It is one. It has been running a single program since the Big Bang, using every physical interaction as a step in the calculation. What the universe is computing is an open question. Lloyd does not answer it. He simply establishes that the question is legitimate and that the scale is definite. Now place our quantum computers inside this picture. We are building devices that operate on the same physical principles as the universe's own computation. They use the same quantum mechanical rules, the same entanglement, the same superposition, the same interference. They are not modeling the universe's computation from outside. They are participating in it, adding their operations to the total, becoming, in a small but physically real sense, part of the universe's ongoing calculation. Which raises a question I do not have an answer to, and that I think deserves more attention than it gets. If the universe is computing something, and we add our own quantum computation to that process, do we change the output? Is the trajectory of the universe's calculation altered by what we compute inside it? And if so, in what direction are we pushing it? Hugh Everett left academic physics in 1957, the year his dissertation was dismissed and never returned. He went to work at the Pentagon, building mathematical models for nuclear targeting strategies. He was good at it. He was good at most quantitative things. He drank heavily throughout his adult life. He smoked constantly. He told his family that he believed the many worlds interpretation was correct, and that therefore death was not an ending but a branching. That some version of him would always continue in some branch of reality. His daughter Elizabeth wrote in her diary as a teenager that she wanted to commit suicide and meet her father in a parallel universe. She later struggled with mental illness for years. His son, Mark, became a musician, formed a band called Eels, and has spent his career processing the experience of growing up with an absent, brilliant, broken father. Hugh Everett died in 1982 on his couch of a heart attack. He was 51. By his own request, his body was cremated and his ashes were thrown in the trash. Because in the many worlds interpretation, it did not matter what happened to any particular physical configuration. Somewhere, in some branch, he is still alive. Somewhere he is watching the technology built on his mathematics become the most consequential engineering project of the 21st century. The many worlds interpretation he proposed in that dismissed dissertation is now cited in the engineering documents of companies worth hundreds of billions of dollars. The idea Bohr rejected is the idea the machines require. What does it mean that the people who build the future so rarely get to see it? And what does it mean that the branch where Everett was believed turned out to be this one? David Deutsch does not fly on airplanes. He rarely leaves Oxford. He works at night. He has described himself as someone who finds it easier to think about abstract structures of reality than to navigate the practical requirements of ordinary social life. He is also, by most accounts of people who work in quantum computing, one of the 2 or 3 people most responsible for the fact that quantum computers exist as a field of inquiry at all. His 1985 paper laid the theoretical architecture. His subsequent work on the constructor theory of information has continued pushing at the same question from different angles for 40 years. What I find striking about Deutsch is not the eccentricity, which is common enough among theoretical physicists, but the completeness of his conviction. He genuinely believes that the many worlds interpretation is correct, not as a working assumption, not as a useful framework, as a description of actual reality. He believes that when a quantum computer runs, the computation happens across a vast number of parallel versions of the universe, simultaneously, that those parallel instances are as real as this one, and that the machine is genuinely reaching into that parallel structure and extracting answers. He believes this the way most people believe that the chair they are sitting on is real, and the machine he helped design works. It gives correct answers. It outperforms classical computers on problems that can be independently verified on small scales. If the machine works and the only coherent explanation for why it works requires parallel universes, what exactly is the reasonable position to hold about parallel universes? And what does it mean that the man most responsible for the machine has held that position quietly from a house in Oxford for 40 years? In December 2023, IBM unveiled a processor called Condor with 1,121 qubits. In 2019, Google's Sycamore had 53. In 4 years, the number of qubits in a leading processor grew by a factor of more than 20. That rate of growth is not linear. It is not even cleanly exponential in the way Moore's law described transistor growth. It is faster than the projections that most quantum computing researchers were making in 2015. The number of qubits is not the only metric that matters. Error rates, connectivity between qubits, the depth of circuits that can be run before decoherence destroys the computation, all of these matter as much or more. But the trajectory of qubit counts is a signal about the investment and engineering momentum behind the technology. And investment and engineering momentum have a way of compounding in ways that are difficult to predict from the current position on the curve. The history of exponential technologies is a history of underestimating the back half of the curve. We are good at predicting the next doubling. We are poor at predicting what the 15th doubling looks like from the third. 15 doublings from 53 qubits is approximately 1.7 million qubits. Most estimates place the threshold for breaking RSA 2048 encryption somewhere between 1 million and 4 million physical qubits, depending on error correction requirements. The arithmetic is not a prediction, it is a rough triangulation. But rough triangulations have a way of becoming more precise as the data points accumulate. What does the curve look like at doubling 20? And who is watching that curve most carefully right now? In 1989, the mathematician and physicist Roger Penrose published a book called The Emperor's New Mind. The argument at its center was this: human consciousness cannot be computational in the classical sense because human mathematicians can recognize the truth of certain statements that no classical algorithm can prove. Penrose was drawing on Gödel's incompleteness theorems, the same results that Tegmark's mathematical universe runs into. His conclusion was that the brain must be doing something that classical computers cannot do. And the only physical process he could identify that might account for this was quantum mechanics. Working later with anesthesiologist Stuart Hameroff, he proposed that quantum computations occur inside structures called microtubules inside neurons, and that consciousness arises from this quantum processing in a way that is fundamentally non-algorithmic. The hypothesis remains deeply controversial. Most neuroscientists find it unlikely. Most quantum physicists find the brain too warm and wet for quantum coherence to survive long enough to matter. But the controversy is scientifically legitimate rather than philosophically dismissible. And here is why it matters for our conversation. If Penrose is even partially right, then the boundary between quantum computation and consciousness is not a boundary at all. The brain may already be a quantum computer. We may have been running quantum computations for as long as minds have existed. What we are building in refrigerated chambers may not be something alien to human experience. It may be a crystallized, engineered version of what thinking already is. And if that is true, what does it mean to build a machine that thinks more powerfully than we do by the same physical mechanism we use to think at all? The public argument between Google and IBM over quantum supremacy ran for years and generated significant coverage. most of which focused on who was right about the specific numbers. Google said 10,000 years. IBM said 2.5 days. Both numbers have been revised since. But the argument itself, the visible public disagreement between two of the largest technology companies in the world, contains a signal that is more important than either company's preferred headline. When two organizations with strong incentives to claim leadership in a field argue publicly about the size of an advantage, rather than whether an advantage exists, you're looking at a consensus wearing the costume of a dispute. Nobody at IBM argued that Google's machine showed no quantum advantage. Nobody at Google argued that IBM's challenge was technically baseless. They argued about magnitude. That argument is evidence of how fast the field is moving and of how much both companies understand to be at stake. The organizations that are not arguing publicly, the ones we do not hear from because their work is classified or because they have chosen not to announce results, are the ones worth thinking about most carefully. The public frontier of any technology is almost always behind the actual frontier. The gap varies by field and by how much incentive there is to keep progress quiet. In quantum computing, some of the most significant potential applications, breaking encryption, secure communications, modeling physical systems relevant to weapons development, are exactly the applications where the incentive to be quiet is highest. What is the actual frontier? How far behind the public announcements are the classified programs? And who decided that we do not get to know the answer to that question? 10 years before Shor published his algorithm for breaking encryption, two researchers named Charles Bennett and Gilles Brassard published a protocol called BB84. It is the first quantum cryptography protocol in history, and it works on a principle that is almost elegantly paradoxical. The same physics that makes quantum computers capable of breaking classical encryption also makes a new kind of encryption physically unbreakable. The key insight is this: in quantum mechanics, measuring a system disturbs it. You cannot observe a quantum state without affecting it. BB84 uses this as a security mechanism. Two parties share a secret key by sending quantum states, individual photons, over a fiber optic line. If anyone intercepts and measures those photons to steal the key, the act of measurement necessarily disturbs the quantum states. The disturbance shows up as errors in the transmitted data. The two parties can detect the presence of an eavesdropper by checking their error rates. If the errors are above a certain threshold, they know someone was listening. They throw away that key and try again. The eavesdropper gets nothing useful and reveals themselves in the attempt. The security of BB84 does not rest on computational difficulty. It rests on the laws of physics. No amount of computing power, quantum or otherwise, breaks a system whose security is guaranteed by the fact that observation disturbs the thing being observed. What I find remarkable about this is the symmetry. The same phenomenon, the quantum nature of information, simultaneously makes our existing encryption fragile and provides the only kind of encryption that is provably permanent. The universe handed us the lock and the skeleton key at the same time. The question is simply which one we use first. In the summer of 2017, a team of Chinese physicists used a satellite called Misius to conduct a quantum encrypted video call between Beijing and Vienna. The distance was approximately 7,600 kilometers. The call lasted 75 minutes. The encryption was guaranteed by the laws of quantum mechanics rather than by mathematical complexity. This was not a demonstration in a controlled laboratory. It was a real communication between real cities on opposite sides of the planet, protected by a physical law rather than a mathematical assumption. Misius had been launched in 2016 specifically to test whether quantum entanglement and quantum key distribution could work at satellite distances. The answer was yes. Entanglement does not weaken with distance. The quantum states transmitted between ground stations and the satellite maintained their integrity across the full 1,400 kilometers of the satellite's orbital altitude. China has since announced plans to expand this infrastructure. A quantum internet, One where communications are secured not by computational hardness, but by physics is being built. Not planned, built. The implications branch in two directions simultaneously. On one side, communications that are genuinely immune to quantum decryption, a solution to the problem Shor's algorithm created. On the other side, a network infrastructure that operates on quantum principles at a global scale, creating new possibilities for distributed quantum computation and entanglement-based protocols that we have not yet fully worked out. What does the internet look like when its physical layer is quantum rather than classical? What becomes possible on a network where the connections between nodes are maintained by entanglement? And who controls the satellites that hold those connections together? We started with a number, 200 seconds against 10,000 years. A gap so large it seemed like a measurement error rather than a physical fact. But it was not an error. It was a data point. And every data point we have examined since has pointed in the same direction. The machine works because it borrows resources from parallel versions of reality. Deutsch showed this in 1985, and the machines confirm it every time they run. Information is the primary substance of the universe. Wheeler spent 60 years arriving at this conclusion, and Landauer proved it has a measurable physical cost. The boundary between computation and reality is not a boundary at all. Zusse intuited this in 1969. Wolfram formalized it in 2002. Tegmark extended it in 2007. Lloyd calculated it in 2006. Everett died, not knowing his mathematics would become an engineering requirement. His idea was dismissed as too strange to be useful and turned out to be too fundamental to avoid. The machines are growing. 53 qubits in 2019, 1,121 in 2023. The curve does not flatten on its own. The encryption that protects modern civilization was designed before Shor published in 1994 and has not fundamentally changed since. The quantum internet is being built in orbit, while most people discuss quantum computing as a future problem. And underneath all of it sits a question that I think we have been circling for this entire conversation without quite landing on directly. We built a machine that works by interacting with parallel versions of reality. We do not know what those interactions look like from the other side. We do not know what a computation looks like in the branches that contribute to our answer and then go unused. We have never asked whether the act of quantum computation has consequences in the parallel instances it draws from. We have never asked because we assumed those instances were not real enough to matter. But the whole point, the entire foundation of why the machine works, is that they are real. They are real enough to compute with, which makes them real enough to wonder about. The machine is running right now somewhere in a refrigerated chamber, pulling answers from places we cannot see, and we do not know what we look like from there.